You know, for years, quantum computing has been this holy grail for the world of finance. We're talking about the power to solve problems so ridiculously complex they could literally bring global markets to a standstill. It's a potential revolution in how we calculate risk, how we price assets, and how we model the future. So yeah, let's just dive right in.
But here's the big one, right? The billion-dollar question that's kind of kept this whole revolution just over the horizon. Are the machines we have today, right now, actually ready for the unforgiving, high-stakes world of finance? Or is this all still just a distant dream? Well, this explainer is going to get right to the heart of that.
So, where would you even start with this incredible power? Well, one of the absolute biggest and most complex challenges is credit risk analysis. We're talking about figuring out the odds that a borrower or even a massive portfolio of loans is going to default. If you get that wrong, it can cost billions. So yeah, it's pretty much the perfect target for a quantum leap forward.
And the reason why is really simple: speed. The promise of quantum is being able to just chew through these unbelievably complex financial models, with tons and tons of variables, exponentially faster than even the beefiest supercomputer we have today. This isn't just a little bit faster, it's a total game changer.
But that brings us to a huge roadblock. See, there's a big difference between the perfect quantum computer you draw on a whiteboard and the ones that actually exist in labs today. And that difference really can be boiled down to one single word: noise.
Right now, we're living in what's called the NISQ era. That stands for Noisy Intermediate Scale Quantum. The best way to think of these machines is like brilliant but really temperamental geniuses. They have incredible computational power for sure, but they are also super sensitive and just prone to making mistakes.
So what even is this quantum noise? Honestly, the best analogy is just plain old radio static. You're trying to tune into a station, but all this hissing and crackling gets in the way. That's noise. It's random interference from the environment that just messes with the super delicate quantum state of the computer. And boom, your calculation is corrupted and the final answer is totally unreliable.
And this really shows you the contrast perfectly. On one side, you've got the dream machine. It's precise, it's stable, it's fault-tolerant. But on the other side, you have the NISQ device we're working with today. It's error-prone, incredibly sensitive, and fundamentally unstable. That's the gap everyone is trying to bridge.
So, how in the world do you get a reliable answer from a machine that's inherently unreliable? Well, that's where a team of researchers came up with this really ingenious plan. The idea wasn't to eliminate the noise, but to actually work with it, to, tame the quantum machine.
This was a brilliant collaboration between the University of Naples' Federico II and a company called 0.2G2Q Computing. They decided to tackle this problem head-on, and they developed what's called a hardware-aware approach. It's a really clever way of saying they basically tailored their software to the specific, unique imperfections of the actual hardware they were using.
Okay, so their method breaks down into 4 key steps. First, they adapt the quantum circuit, that's the sequence of operations, for the financial model. Then, they use a noise-aware training strategy, which basically teaches the algorithm to expect and work around the hardware-specific flaws. After that, they meticulously calibrate the physical quantum gates. But the real secret sauce, the step that pulls it all together, is a process called tailored transpilation. Now, transpilation, it's more than just compiling code. Imagine trying to translate a book. A simple compiler would just translate it word for word. But a skilled translator, a transpiler, they would adapt the story, the idioms, the phrasing, so it fits perfectly with the local dialect and culture. That's exactly what this process does. It rewrites the quantum algorithm to run perfectly on one specific machine's unique layout and all its little flaws.
So, with this clever plan all set, it was time for the moment of truth. Could this hardware-aware approach actually work on a real quantum computer to solve a real financial problem? It was time to run the first proof of concept.
The mission was crystal clear. Use a real, noisy, superconducting quantum computer to accurately model a standard normal distribution. Now, this is a fundamental building block for calculating credit risk. If you can model this thing perfectly, you can make much smarter, much safer lending decisions. This was the real acid test.
And hey, this wasn't just some simulation. They used a real piece of hardware, the Italian superconducting quantum computer. Its name is PartNope. They ran a powerful algorithm called quantum amplitude estimation, which is a core technique for calculating a value with high precision. And the target, of course, was that all-important normal distribution.
So, did it work? The results were a resounding yes. In their own words, the experiment demonstrates the viability of quantum adaptation on a small-scale, proof-of-concept model inspired by financial applications.
The point is, they actually did it. They got a useful, accurate result from a noisy, real-world machine.
Look, this is so much more than just one successful experiment. This breakthrough signals a major shift in how we think about the entire field of quantum computing. It's opening up a whole new frontier of what's possible, like right now.
So what are the big takeaways here? Well, first, we don't have to wait for perfect machines. We can get real value from these noisy NISQ devices today. Second, customizing your software for the specific hardware, that's the key to unlocking performance. This work also builds this critical bridge between the theorists designing algorithms and the engineers building the machines. And finally, this is a huge first step towards using quantum computers to calculate really complex risk metrics, like value at risk, the gold standard on Wall Street.
At the end of the day, the core message here is a really powerful one. The future of quantum finance isn't about waiting a decade for some flawless, fault-tolerant supermachine to show up. No, it's about being clever right now and finding ingenious ways to make today's imperfect, noisy machines do incredibly useful work.
And that really just leaves us with a fascinating final thought. I mean, if a team of researchers can already tame a noisy quantum computer to solve a key piece of the credit risk puzzle today, what other massive financial challenges are we going to solve tomorrow?